Thank you, Ashley. Good to see you all today again. Friday afternoon, it's a hard lift to talk about statistics on Friday afternoon, isn't it? Or at least it's afternoon for me. I know maybe it's Friday morning for some of you, and maybe that makes it better. I'm not sure. Before I start, I just wanted to have a check-in and see if there's any questions or points of clarification or ideas based on our discussion on Wednesday about measures of occurrence and measures of association and relative and absolute scales and such. Anything rose to the top as you were going to sleep on Wednesday night? While you're thinking about that, I will share screen. Just get my monitor set up here. Okay, so Ashley, I do have my chat window open, but I only seemed moderately successful on Wednesday in paying attention to it. So if there's anything that's in the chat and I don't seem to notice it in a minute or two, let me know.
I can do that.
Great, thank you. Okay, so what we're going to talk about today is really a kind of next step in the process from thinking about measures of association, and that's thinking about multivariable analysis. So we're going to This is actually a topic that you could spend an entire semester on, or maybe you would learn some of these ideas over the course of several different courses over several different semesters. So I'm saying that in advance to say I'm trying to kind of touch on sort of a big picture strategy and also a few specific kind of hands-on skills. But if you feel like there are parts of what we talk about today that don't entirely click, I wouldn't stress a lot about that. If you feel yourself getting lost, step back and ask yourself, what's the big picture here? What's the big question? What are we trying to do? Because I think the process of learning how to go from epidemiologic questions to epidemiologic answers is one that happens over time for all of us. And it happens through learning things like this, but especially through practice, which is another reason to plug reaching out to any of us with specific questions you have about analyses you want to do. And one great opportunity coming up is that roundtable on multivariable regression that Mike's going to lead next week. So that's just to say, don't get lost in the weeds. If you feel yourself in the weeds, step back and wait a few slides and let's see if we can reorient. Okay. So here's my thought for our objectives for today. I want to describe this general approach to the use of multivariable analysis for etiologic epidemiology, so for an analytic approach rather than just a descriptive. We want to touch on, maybe review for many of you, some common sources of systematic bias error that we can address with multivariable analysis. And then I want to just have a brief discussion about variable selection strategies, which is basically how do you pick what you should adjust for or stratify on. How should we do that? All right, so on Wednesday, we had this this slide, kind of one way of representing the spectrum of what we all can do as epidemiologists. On the left-hand side, doing purely descriptive work. In the middle, some hypothesis generating or prediction or maybe outbreak investigation that's kind of beginning to use multiple variables. And on the right-hand side, causal effect estimation and program evaluation, particularly quantitative outcome evaluation. So this spectrum of things. Now the descriptive epi, if we think of kind of the two things that often are used as the definition of epidemiology, the descriptive epi is really about characterizing the distribution of health in populations, which is really critically important, understanding the risk rate or prevalence of disease in a population and how it's changing over time, for example. But typically, when we're looking at descriptive epi, we're usually looking at one or two variables, one variable at a time, maybe with time included or something like that. We're usually reporting the world as it is, rather than trying to estimate some underlying feature. So we're reporting the world as it is, and we're using the numbers that we collect through our surveillance systems. And the analytic tools we have for this are some of the things we talked about last week or last time on Wednesday. So our measures of occurrence like risk or prevalence or rate, measures of association like the risk ratio or risk difference or prevalence ratio or prevalence difference, measures of impact, like the percent population attributable fraction, or something like trend analysis, looking at trends over time. So we've got really a range of tools that we can bring to bear. Generally, though, undoubtedly we could come up with some exceptions, but generally we do not use statistical adjustment like multivariable analysis when we're doing purely descriptive epidemiology. One exception sometimes people raise when I say that is, oh, well, we do age-adjusted rates in our surveillance reports. And that's true, that it still seems like a descriptive process and you are adjusting or standardizing for something like age. But I would argue that that is actually beginning to tread into that area of multivariable analysis, because what you're doing when you adjust for age is you're saying, I would like to know what the pattern was net of or conditional on the age distribution. So when you begin to have that sort of language and those sorts of conversations, you're moving into multivariable, and you're moving at least incrementally away from descriptive epi and towards something like analytic epi. Again, these aren't just dichotomous binary. This is a spectrum, so it doesn't have to be one or the other. So in analytic epi, in descriptive, we were talking about the distribution of health in populations. In analytic, we're trying to understand the determinants of health in population. So that is both the causal mechanisms, but also importantly for applied public health, what are the opportunities for intervention? What are the modifications or interventions that we can do that will have an impact on health? Now, in the kind of umbrella of analytic epi, there's two kinds of strategies people use. One is predictive, and that's basically this process of saying, how could I do the best job of guessing the value of the very next observation to come along? Like, how could I maybe predict what the preterm birth rate is going to be next year based on the information I know about the past, for example? That's in contrast to an etiologic model where really the motivation for the question is, what is the true causal association that is underwriting this process that's going on? I make this distinction here because I'm going to mostly talk about etiologic models where we're thinking about cause or mechanisms. And the reason that's important is because our concern about bias is specific. There's specific concerns about bias when we're talking about etiologic models that might not be true in predictive models. And our tools, if we think about analytic epi, start with study design. How we design any kind of epidemiologic study has a huge impact on the kind of inference we can draw from it. So randomization or some sort of natural experiment is a very powerful design for establishing or evaluating causality. But we can do other things like stratified analysis, stratifying on a confounder, so trying to address some sort of bias, multivariable regression, and then there's fancy things that I'm not going to talk about today, like G methods for causal inference. All right, so there are lots of kind of recipes and steps for how we might do epidemiologic analysis, but Sandro Galea and Catherine Keyes wrote this nice book, Epidemiology Matters. I like it because it tries to sort of boil a lot of methods down into some pretty sensible steps that are focused really on the idea of performing or carrying out consequential epidemiology. In other words, identifying questions, not just because they're interesting, but because they're actually, the answers to those questions can actually impact the health of populations. And so they have these 8 steps, and they sort of divide them into the steps that are the descriptive part of the process, which we need to start with. Even if we're doing analytic epidemiology, we still need those first steps. And then the steps that are specific to analytic epidemiology. And then I'm not really talking today about the dissemination of results. So I'm going to go through these steps through the course of today and sort of use them to think about how do we approach an epidemiologic analysis with a particular question in mind. And the question is really critically important. So it starts with a question. If we start with data and we just try running stuff, we just look to see what we're going to find, we end up with a big mess. We end up with a mess because we don't actually have clarity about what it is we want to know, or what we anticipate or expect might be going on, or what theoretical construct we're trying to test, what program we're trying to understand. So we really want to be clear about what is the question, because if we're clear about what is the question, the steps of the analysis fall much more coherently from the question. If we're not clear, then we end up just running a lot of SAS code and not really being sure what we get in the end. So this PICO acronym we introduced on Wednesday, this is just one way to form a question. If you have these 4 pieces, you can form a question. If you can describe the population, if you can describe the focal group, which is sometimes called the exposed group, or maybe it's the group that received the intervention or participated in the program. You need to compare them to somebody. Remember, with our measures of association, we want to know, did the focal group have the same experience of health as the comparison group or a different experience? And then, of course, we're motivated by the health outcome. So we want to be clear, what is the health outcome? Now, sometimes we have lots of things that might be exposures and lots of things that are outcomes. It's not that you're only allowed to be interested in one thing, but when you're doing one analysis, there should be one pretty clear goal in mind. And so the more specific you can be on these, the better. And then, as I said, we really want it to be a consequential question. There are lots of things that many of us in academic and applied public health do that answer questions that are interesting, but don't necessarily translate into any clear action. Sometimes those are valuable. We can't always predict how a little bit of information is going to be used in the future. But a lot of times we want to we want the most bang for the buck. And that means thinking about what is the question for which the answer could actually influence policy, program, activities, etc. So a consequentialist question. When we talk about the answering that question, we're often talking about describing, understanding, interpreting those measures that we introduced on Wednesday. So like the magnitude of them, how big is the measure of association? The direction, in other words, did the exposed group have a worse health outcome compared to the referent group? Or did the exposed group have a better outcome compared to the referent group? So that's direction. Was it positively associated with the outcome or negatively? And then statistical significance is another thing that gets talked about a lot, and I'm going to give my little spiel about statistical significance towards the end. All right, I'm going to show a few kind of silly slides that are perhaps not the most consequential questions, but are interesting data findings. This is somebody who didn't start with a clear question and instead started looking for how things go together. What we have here is the temporal correlation between the divorce rate in Maine and the per capita consumption of margarine. Clearly, both are going down, which is very interesting. This is the US spending on science, space, and technology, and it's strongly correlated with suicides by hanging, strangulation, and suffocation. Sometimes spending on science, space, and technology does make people feel upset. Per capita cheese consumption is strongly correlated with the number of people who died by becoming tangled in their bed sheets. I just want to point out the axis over here for bed sheet tanglings ranges from 200 to 800 per year, which to me seems like an incredibly large number for strangulation by being entangled in your bed sheets. The age of Miss America is correlated in an interesting pattern with murders by steam, hot vapors, and hot objects. And then finally, and very important in our modern times, it is clear that global warming, as it goes up, is strongly inversely correlated with the count of pirates. And so maybe one of the solutions to global warming is to have a return of the pirates. All right, so we've all heard and often maybe say this phrase, correlation is not causation. That when we observe two things to be associated with one another, that doesn't mean that one causes the other. Sometimes in epidemiology, people feel very comfortable just having correlations. I would argue that even though it's so hard and sometimes maybe impossible to have clear causation, that when it comes to etiologic analysis, causation is almost always what we're after. In etiologic epidemiology, correlation is we only measure the correlations because we hope they tell us something about causal structures. So we know that correlation is not causation, but I would argue that causation is what we want. Correlation is not adequate. Knowing something about margarine in relation to bedsheet entanglement is strongly correlated, but it was never a question that really needed to be asked, and the answer clearly doesn't inform anything useful for us. So if we say that correlation is not causation, well then what is correlation, right? Because clearly I just showed you a bunch of examples that have strong, real, I mean the correlation is real, statistical correlation. So if it's not a cause and effect, what is it? Well, here's just a few examples of why we can have correlation. Of course, one thing is chance, random error. This happens a lot, especially if we have sort of small sample size. We might just have had bad luck or good luck, depending on how you look at it. If you got a significant value and you feel really good about that, but it might be chance alone that gave us the correlation, but that the truth isn't, those two variables are not correlated. Of course, the thing, as I said, that we really want to know is causation. We would actually, when I say we would want to know it, what I mean is we would want to know whether or not, for example, X causes Y. It's not that we want to prove that X causes Y. We want to know the truth. Does X cause Y? Another thing that happens a lot, and this is a problem in MCH, sometimes because we rely a lot on cross-sectional data, is the possibility of reverse causation. X and Y might be correlated, but it might be Y that came first. The outcome actually caused the thing that we're measuring as the exposure. And then there's two sources of bias I have here. We're going to spend a lot of time today talking about confounding. And in the pre-lecture slides and video that many of you watched, I introduced the idea of collider stratification, this thing here. And I'm going to mention it just a little bit more at the end. It's a little bit more of an advanced topic, and we can talk about it more later if people want to know more about collider stratification. But all five of these are explanations or reasons why we might have correlations. And of course, what we want to do is we want to distinguish of these five things, when do we have a correlation because there's actually a causal effect, and when is it not because of these other reasons? And that's a tall order, to be quite honest. Sometimes, I mentioned that some people sort of feel very comfortable saying, I only care about correlation, I don't care about causation. And I think mostly that's a way to use language to represent the fact that I know that causation is hard and I can do correlation, so I'm just going to do that. Again, I would argue that, if you think of the structure of a scientific paper, how there's like intro, methods, results, discussion, I think in the methods section, we should be extremely causal. In other words, the thing that we try to do is estimate causal effects. In the results and discussion section, we should be much more cautious. We should talk about correlations and associations. In other words, we should both try to be causal, and we should recognize how difficult that is and that there may be limitations in our findings. This just is some words that sometimes people use. And if you're using word like effect or determines, those are words that sound like you're implying causation. And if you're using association or correlated, those are less causal. They don't mean it's not causal, but they're not sort of implying as much. So sometimes the language we use, again, when we're writing out kind of the plan, our goal is one sort of thing. And then the language we might use in reporting the results, like on in an infographic or in some sort of surveillance report, are slightly different. Okay, so what we're going to do for the rest of the time is work through an incredibly simple case study that's sort of related to something we did on Wednesday, and use this case study to just unpack some of the issues about how do we approach this kind of quantitative analysis of an epidemiologic question. The case study is overly simplistic. You will have questions that are more complicated than this. That's when we should all have more conversations about, okay, so how can the simple situation translate into the situation where there's more variables, more complicated measures, et cetera. So the story is about rural-urban disparities in preterm birth. So imagine in state X, your state, it has been reported through surveillance reports, or you just observe by describing the data as we see it, not without any fancy statistical model or anything, just here's what we see, that women who live in rural counties have higher risk of preterm birth than women who live in urban counties. All right, so this is what we see. So let's do what we did before. Let's use your annotation tools, and let's just do a little bit of brainstorming together. What are possible reasons that we might observe a rural-urban difference? We could say it's a risk difference, or it could be a risk ratio, where women living in rural areas have higher risk than urban areas. And there could be reasons that are non-causal, in other words, like sources of bias or error, but there could also be causal reasons. Good. So let's just spend a minute or two doing that. I'm going to turn off the annotation names again. All right, so a couple causal reasons. It could be that there are things that are different and tied to rurality that affect preterm birth. So fewer high-risk OBGYNs in rural areas, less access to care, transportation issues. Anybody have any non-causal reasons? I actually think there's a couple in the causal list that I would, we'll talk in a minute about what the definition of cause is, because sometimes it's hard to think about which part is the causal part from rural urban to preterm birth and which part is the non-causal part. So somebody says maybe transportation is over in the non-causal. Okay, interesting, yeah. Okay, younger age over there perhaps. Any other thoughts? Oh, and there's stuff in the chat too. Am I missing anything? Oh, there's.
That was just the fun from.
Oh, the pirates. Okay.
Yes.
Oh, yes, Nicolas Cage movies and ice cream sales. Well, that could be causal. You never know. Yeah, ice cream when they go to them. Yeah. Okay. So this is, yeah, okay, good. More land, misclassification of, I'm not sure if unemployment was with the misclassification or if that's a separate one. Good. So I actually picked rural urban, which is not a variable, a measure that is inherently true about an individual. Instead, it's something that describes their context. I picked it a little bit on purpose because it's a little more challenging than if we said smoking was the exposure, which is something that is about an individual, although it's influenced by lots of things outside the individual as well. And this idea of a rural-urban difference or a geographic disparity is similar to some of our conversations we've had before about how do we think, maybe causally, about what health disparities mean. So if we think about rural-urban, in my mind, and you can continue to add things if you want, I would think rural-urban are what are the characteristics about the rural places that shape the health of women. And so I think the younger age, probably, I agree, I would put over in the non-causal reasons. There could be age differences in rural and urban areas, and those might be a non-causal or a spurious reason that we see in association. Whereas transportation or access to care might be features of a rural area that are sort of created by the ruralness, right? There's something about both the historical nature of how that place remained rural, whereas other parts became urban, and also just the social and economic dynamics of the rural-urban spectrum. So things like higher rates of smoking or younger age might be considered non-causal reasons, and less access to care, including fewer high-risk OBs and transportation, might be more causal. Now, having said that, we could actually have lots of interesting discussions and arguments about whether there is something about ruralness that drives out-migration of young people, and that the age differences are actually a function of ruralness rather than some other process. So perhaps age distribution is a mediator and not a confounder. So I'm going to talk about the mediator confounder thing and that more. But this is great. Thinking about ideas of why might we see a correlation and which parts of the correlation might be because of causal reasons versus non-causal. All right, let me just clear these. Thank you for doing that. All right, so I had we might see the correlation for two reasons. One is that it's spurious, so we're comparing apples to oranges. Maybe there's just a range of things like age distribution or smoking or education distribution that are different between rural and urban areas, and it's not really about, for example, the healthcare environment. On the other hand, maybe it is about health access or the social and economic opportunity that's available in rural counties. So this first one is an argument for it's not real, it's correlation, but not causation. The second one is maybe it is real. So if we go to our question, we want to form this as a clear question so that, as I said, our analysis can kind of flow from that. So our population, let's say we're going to do all pregnancies that ended in a live birth in 2015 in my state. So that's the population. We talked on Wednesday about how populations, we can think of them a little bit more dynamically than that, and thinking about the sort of the construction of population and the relational nature of populations. And so we could revisit this when we think about what does it mean to be a pregnant person in a rural county and be a pregnant person in an urban county, not just in terms of the pregnancy, but also in terms of one's relation to your community and family and other forces. But for now, I'm going to leave it at this kind of cut and dry. These are the people who are the population. We're making this pretty simple. So we're just divided the state into counties that were designated as rural as compared to counties designated as urban. And as I said, the outcome is preterm birth. Now, having done this, we actually could ask a lot of kinds of questions with this PICO acronym. We could ask a simple descriptive question, which again is describing the world as we see it, right? Is the risk of preterm birth among pregnancies ending in my state equal in rural as compared to urban counties, or is it unequal? So that's a descriptive epi question that could have an answer. Or analytically, etiologically, maybe what we want to ask is, what is the magnitude of effect of residents in a rural as compared to urban county on the risk of preterm birth among pregnancies ending in live birth in my state? And so when I use the word effect, I'm implying something causal, which is to say, I want to know what's the measure of association after I've eliminated all the possible sources of error. Spoiler alert, I can't eliminate all the possible sources of error, but I'm going to do the very best I can to eliminate sources of error that I'm aware of. But that's what we mean when we say the magnitude of the effect. What we'd like to do is estimate not just what we see, but what portion of that, if any, is true because something about the rural environment actually causes a different kind of pregnancy outcome. All right, so let's revisit our 8 steps. So remember, the first 4 were part of descriptive epi, but they're still necessary for analytic. And the reason is because they're about establishing our understanding of what it is we're even doing, right? They start off with defining the population, which we did, conceptualize and create measures of exposure and outcomes. So we've got our measure of our exposure, rural, urban, and outcomes preterm birth. Take a sample of the population. Now, a lot of times in MCH, we actually do population-based work, right? Our vital records are 99, like our birth certificates are 99.5% of all live births get registered on a birth certificate. So some people would say, well, you don't have a sample, you have a census. But I think most of the time, I still sort of think of it as a sample because we can only take so many years. In this case, I said I was going to do 2015. So it's just 2015, which I can imagine as a sample out of all possible years, for example. Or it's a sample out of all births in the whole US. I just took the sample from my state, for example. So somehow we take a sample of the population. When I say describe its characteristics, that means not only how many are rural and urban and how many have preterm birth, but also other things like age and smoking and education. And then finally, this is basically where we got to on Wednesday, estimate measures of occurrence. So let's look at what we got. This is from a simulated data set. So this is not all true in the real world, but it is it approximates some true data. So this is the data that I'm going to use throughout. This just shows the breakdown. I've cut out a little bit of the information from Wednesday because this is just a review of that part. So the 0.25 means that there's a 25% risk of preterm birth in rural counties compared to only a 15% risk in urban counties. Now, if you follow preterm birth epidemiology, those are both relatively high, perhaps implausibly high, some might say, but let's just go with that. Okay, so we've got these numbers. Clearly, this descriptive story is that there's much more risk for preterm birth in rural counties as compared to urban. So just connecting this to our PICO question, we've got our exposure, our outcome, our measures of occurrence, our sample of the target population. Okay, so we estimated the measure of occurrence, which was, remember, measure of occurrence is like risk, prevalence rate, et cetera. So we estimate that. We know it not only in the total population, but also separately in the exposed and unexposed. Now we want to do what we learned on Wednesday, estimate measures of association between exposures and outcomes. So now we're taking the two variables, the exposure, rural versus urban, and the outcome, preterm versus term, and we're saying, well, do the two tend to travel together? Are they correlated? Does it seem that preterm birth is more common in one place than another? We just saw in the previous that it's quite obvious it is. What we actually want is a number to quantify how much so. And so we could calculate the risk ratio, which in this case is 1.73, or the risk difference, which is 0.108. Remember the interpretation of the risk difference. This basically means there's an additional 10 or 11 preterm births per 100 live births. So a 10 or 11% higher risk in rural of preterm birth in rural counties as compared to urban counties. We always have to say that as compared to, otherwise you wouldn't know 10% more than what. So it's 10% more in rural than in urban. Or said in relative terms, there's 73% higher risk, or 1.73 times the risk of preterm birth in rural as compared to urban. Now, these are, again, are where we ended on Wednesday, and we would maybe call these crude or unadjusted. And what I mean by that is we haven't done any statistical hocus pocus to them. These are the numbers that you counted up from your vital records. So they're the snapshot, the picture of how we observe the data. It's the surveillance picture. They're not adjusted. So our question, of course, is, well, that's interesting. Is it causation or is it correlation? Is there some non-causal reason why that occurred? All right, so the next two steps of the analytic epi are about two really key ideas in describing and understanding how cause can work and how we can look at our data to understand that. The first one's going to ask about something called effect modification, which I'll talk about in a second. And then the second one is about bias and in particular confounding. All right. I would argue that it's really hard for any of us to actually start to analyze data and think about those two things that we're going to talk about, which is effect modification and confounding, if we don't have a theory of causation in our mind. What I mean by a theory of causation is, like, what's a plausible way that these variables all fit together? What's a plausible causal structure? And how do you know what a plausible causal structure is? Well, occasionally there are brand new diseases that we know very little about. So when Zika first hit, we knew very little about Zika. And so our causal understanding, or our hypotheses for how Zika might relate to outcomes or to precursors or anything, took a little while to form. But for most health outcomes, we have some amount of evidence, and often we have some amount of theory that lets us say, okay, I think this is a rough approximation of how this could work. And then based on that causal structure, we can begin to examine our data with something as a guiding light, rather than trying to run every possible correlation under the sun and picking the one that we like the most. So starting off with a causal structure means asking, not just, is my exposure causally related to my outcome, but really something like age. Is age an intermediate potentially between rural, urban, and preterm birth, or is age a confounder? What are the other things? Transportation, education, smoking. How do those relate to one another? So we can begin to sort of document what do we already know, and then also be able to use that to make a strategy for how we're going to analyze data. One approach to this causal thinking that has become relatively dominant in epidemiology in the last 15 years, although some people push back on this with valid concerns. One approach is a framework for thinking about what causation means and how to be able to test for it. And it's called the potential outcomes framework. These next two slides are maybe a little nerdy, but this is a kind of a potential outcomes definition of what does cause and effect even mean? What does it mean for something to cause something? So we might say A, if A was an exposure or an intervention, A causes Y, Y is an outcome. If and only if the value of Y is different for at least one individual, when the level of A is set at one level, for example, if the person was made to be exposed, as compared to that very same individual if it was set at a different level, unexposed, everything else being held the same. So the idea of potential outcomes, we would say something is a cause if the outcome would change if you change the exposure and everything stayed identical, including the person themselves. So imagine like Superman, making the world go backwards and reversing time, and then change the exposure and then rerunning time again and looking to see if the outcome was the same as it was with the exposure versus without. Now, obviously that sounds a little fantastical. We could say in this particular setting, the potential outcomes might say rural residence causes preterm birth if the gestational age for at least one individual in a rural area would be different if that very same pregnant person instead lived in an urban area. So if we could keep everything the same except for her exposure. Now, as I said, in the pure form of potential outcomes, the way we have a thought experiment about it is we kind of imagine two parallel universes, right? The universe where everything's going along and you gave the exposure to somebody, you assign them to live in a rural area. And then a parallel universe where all the exact same people and places exist, except you took that person and you made them live in an urban area. And then you look at the outcomes. That's the pure form, which obviously we can't do, but the practical form that we think about with observational research is that referent group, when we're talking about the focal group and the referent group, we want them to be made to be as similar as possible in every possible way, ideally so that the only thing that was different about them was one's exposed and one's not. And in that way, we could say that one group is exchangeable for the other group. We could interchange them. And if we could be so perfect as to get them exchangeable, then all we have to do is look at the difference in their outcomes, and we would have an estimate of the average causal effect. So that's what we're trying to do in etiologic epidemiology. We're basically trying to make the exposed and the unexposed be balanced or similar, equal to one another on everything except for this one factor, the exposure itself, so that we can compare the outcomes. All right. Maybe another way of looking at it is by drawing a picture. And this is what I appreciate that I didn't give you a whole lot of lead time to watch that pre-recorded lecture on directed acyclic graphs. I only gave you a few days, and I'm grateful that many of you were able to watch it, and I recognize that not everybody was, and that's totally okay. It will be up, and you can certainly watch it again after this or watch it for the first time after this. I'm going to give just a couple highlights about DAGs, and in particular, I want to use DAGs to help us think about how are we going to do our analysis. And when I say how are we going to do our analysis, I don't mean just SAS code. I mean, like, how do we pick what variables need to be included to get the estimate that answers the question we want to answer? Okay, so just as a review for some and new for others, this picture that's shown here just looks like a picture that we might draw anytime we're thinking about a conceptual framework. But it's actually a particular kind of graph called a directed acyclic graph. And what's useful about it is that directed acyclic graphs have a set of rules for describing causal relationships. And because the rules are well described and clear, there's actually strategies we can use to look at a DAG and help us uncover not only things that would be obvious without the DAG, but also possibly things that might be counterintuitive or might have been surprising about whether a variable is, for example, a confounder or should not be included. So DAGs represent something about how variables relate together in the world. The way I like to think of it is it's just one guess, an overly simplified guess at how the world works. We don't know exactly how it works. So a lot of times what we need are 2 or 3 or 5 or a dozen DAGs that say, this is one way it might work, and here's another way it might work. And if we had many versions, we actually could then say, okay, well, I'm going to try my quantitative analysis if this version were true, and then I'm going to try my quantitative analysis as if this version were true, and look and see whether or not it gives me a different answer. If it gives me a different answer, I may not know which one is true. I may need information from theory, from prior evidence, from expert knowledge, or I may need future research to be able to distinguish between them. But it gives us a structure for kind of navigating the uncertainty that is just inherent in observational research. When we can't control and randomize everything, then things are messier. And so what we'd like to do is have at least a structure for managing the mess. So in a DAG, directed acyclic graph, there's 2 kinds of things. There's nodes, which I have here as words. They're often just letters. Nodes represents a variable. The variable might actually be in your data set, or it might be a variable that you think is important in the world, but you might not actually have it measured. So you can include things that you don't have because they're important. So nodes, and then edges. These are these arrows. They're unidirectional. So this is called a directed acyclic graph. Directed means that the arrows only go one way. And acyclic means that the arrows imply a temporal ordering, like that this, they also imply causation, but they imply temporal ordering, that this happened before this. If there's a temporal ordering, what that means is you should never be able to follow DAGs in the direction of the arrows and get back to where you started because time went forward. Okay, so that's kind of how DAGs look. When we talk about what kinds of variables, I'm going to tell you towards the end, there's actually 5 kinds of variables we care about in our DAG, but here I'm just showing you 3 of them. There's the exposure variable, the outcome variable, and I'm just generically calling this one a covariate, which means it could be a confounder, a mediator, a collider. It just isn't the exposure or the outcome. It's a third variable. It's really important that we're clear about what the exposure is, because when we think about bias or effect modification or anything, it's always specific to the relationship between the exposure and the outcome. Like one variable might be a confounder for one relationship, but isn't a confounder for another. So we can't just assume that a confounder once, a confounder always. It depends on the specific question, which is why we want to be clear which variables are which. Okay, so I said that our first step was going to be to talk about effect modification. Many of you may have heard of or work already with this idea of effect measure modification. It's also sometimes called interaction. Those are actually 2 slightly different concepts, but they overlap. And so for now, I think I'm fine letting us use those 2 interchangeably, but we can talk later if somebody's interested about the differences between them. In causal thinking, the idea of effect modification. So imagine we had established that there really is a causal relationship between rural versus urban status and the occurrence of preterm birth. Effect modification asks, is the causal relationship the same for every group of people? And in particular, this effect modification is characterized by an interaction between these 2 things: maternal education, so not like the schools, but actually how, like the mom's highest level of completed education, and rural urban. So the question might really be, is there a rural urban disparity for women who didn't graduate from high school and also for women who graduated from college? Or maybe is there only a disparity for women who didn't graduate from high school, but college graduated women have the same risk if they're in rural and urban? So that's the idea of effect modification. It's a third variable that modifies or changes the magnitude or possibly even the direction of the effect. And I think it's super interesting in general. I think it's really interesting when we're thinking about social determinants of health, when we're thinking about community context, the idea that the effect of a social process or a community context might not be identical for every single person. It might be that it's more acutely felt or less acutely felt by one group than another. Maybe one group has more resilience to a negative exposure and one group is more susceptible. So effect modification is a way to dig into those things. So just as a caveat, I have this note down here. I'm not going to make a big deal about it now, but this is actually not a legitimate DAG. You're not supposed to have an arrow that points at an arrow. DAGs don't have a really great way to show effect modification. The way they like to show them, I think, doesn't help for teaching. So when I have this arrow, what I'm saying is the strength of this relationship is different for low versus high education. So I just want to not mislead you into thinking that that's a legitimate DAG. It's a legitimate picture. So how do we do this? How do we look for effect modification? Now you'll notice, you may have already noticed, that I am taking the easy road by only having simple binary variables. The exposure is binary rural urban, the outcome is binary preterm term, and my effect modifier is binary, low education versus high education. Everything we're talking about works if you have more complicated versions of the exposure, the outcome, or the effect modifier. But it's easier to sort of talk through it when everything is made more simple and binary. Okay, one way we could look, I mean, the idea of effect modification is that the question that we're asking when we say, is there effect modification, is there a different relationship between rural and preterm birth for women who have low education as compared to women who have high education? So maybe it's just a no-brainer. What if we just took all of our data and we just split it out into the women with low education and the women with high education, and we just made a separate 2x2 table. And then we could have an answer to the question. And here's what we get. We see clearly that the low education, women with lower education have higher overall risk. So this is as high as a 30% risk of preterm birth. Again, this is simulated data. That's probably implausibly high, versus 20% in urban areas. And here it's 19 versus 11%. And we get these two different risk ratios and these two different risk differences. So they're clearly not numerically equal. The question is, are they meaningfully different? When do we know if we have effect modification? But the thing that we're looking at for effect modification is, do these numbers in one strata differ from these numbers in another strata? Now, I want to say that effect modification is scale dependent. In other words, we can't just look at both of these, 1.46 and 0.095, and ask yes or no, are they equal to both of these? Actually, the answer could be in some scenarios that yes, there is effect modification on one scale, but it's not present on the other scale. So multiplicative is about the relative scale. We talk about multiplicative interaction or effect modification. And that's where we compare the stratum-specific risk ratios. So the 1.46 versus 1.64. If we thought that the difference between these was both statistically important, but really importantly, clinically important, public health important, if these two are meaningfully different, then we would say there was evidence of multiplicative effect modification. Alternatively, and again, the answer could be yes for both of these, no for both of these, or it could be that only one has interaction or effect modification and the other does not. The alternative is on the additive scale. We use the risk differences instead. And here we see a 0.95 versus a 0.73. Now, a lot of times people say we should look at both of these, and it's not a bad idea to evaluate effect modification on both scales. But one thing that's increasingly gaining traction is that when it comes to causal inference, which again is the thing we're trying to do, we're trying to understand whether something about where you live causes your health. When it comes to causal inference, it's actually the absolute scale that probably matters more. So even if your main analysis was using risk ratios, for the specific question of effect modification, you probably want to make sure that you test whether there's effect modification on the additive scale, because that's the one, if there was evidence that these were really different from one another, it suggests that there's something else going on. There's something about susceptibility or resilience or a third variable, or there's something else going on that is making one population be more sensitive to the effects of place than another population. Okay, so again, this idea of how do we know what's enough? So how different is different enough? How different is enough to say, yes, we have effect modification, or no, we don't? The primary way, a primary way is a qualitative difference, which is basically sort of the sniff test. Are they different enough that I would actually come to a different conclusion if I used one strata versus another? So for example, imagine if the risk difference for women with high education was 0. In other words, women in rural areas with a college degree have exactly the same risk of preterm birth as women in urban areas with a college degree. But it was a risk difference of 0.2 for women who didn't graduate from high school, for example. So women who didn't graduate from high school and lived in rural areas have much higher risk than women who didn't graduate from high school and live in urban areas. So that's a situation where qualitatively they're different. And what I mean by qualitative is we actually come to a really different conclusion. In one case, we say it's a null association, and in the other case, we say there's it's a non-zero. There's something going on. But we know that sample size plays a role and precision plays a role. And so what about statistical tests? Now I'm going to tell you in a little bit that we should not use statistical tests for confounding. But for effect modification, it's a fair thing to say statistical tests, including p-values for a test for interaction, can be a useful tool for characterizing whether there's enough information to say these two numbers are different or not. So for effect modification, a statistical test can be also a useful supplemental piece of information. And what I'm going to show you in a minute, I'm not going to show you a lot about it, but how to get from SAS a test for homogeneity using the Breslow-Day test. Alternatively, you can also fit a regression model with an interaction term. I'm going to show you what that looks like as well. So these are two ways to get statistical tests, which should be used together with the qualitative. Let me say one thing. It's possible that sometimes we have evidence, statistical evidence of effect modification. In other words, the p is less than 0.05. But when you look at the two numbers, they're just not that different. Like if we were to have gotten a significant, we're going to find out in a minute whether this is significantly different. But let's say these two risk ratios were significantly different. It's true that it looks like the effect is stronger in high education than low education. But honestly, 1.64 and 1.5, they're just not that different. You know, they're a little different. So I wouldn't be able to make a whole lot of meaning out of what's going on there. Similarly, a risk difference of 0.95 and 0.73, that actually on the absolute scale, that could be meaningful. But it's not like one is positive and one is negative, or one is 0 and one is positive. It's nothing dramatic like that. Okay, so I'm going to show you a couple ways. I guess I'm not showing you how to do the Breslow-Day. To do the Breslow-Day test, I guess I'm showing you that later in the when we do the confounding with proc-freq in SAS, it will give us a Breslow-Day test for homogeneity. So there is a way just with stratified tables using proc-freq in SAS and similar procedures in Stata or in R to get a statistical test for homogeneity, which means the test for whether the two strata are statistically the same. What I apparently am showing you is how to use a regression model in SAS. And in this case, again, this is a simple situation, and our goal for this one model is just to ask the question, is there evidence of effect modification? The reason I put these two models here is because we talked a little bit on Wednesday about how you can use SAS to estimate not only risk ratios and odds ratios, but also the risk differences or prevalence differences. In other words, we sort of were selling the point that absolute measures are really interesting and powerful, but how do we do them in SAS? There are a couple different ways. This is a relatively simple way using the procedure proc-genmod. So proc-genmod is, maybe as it sounds, a general procedure that fits lots of kinds of models, unlike proc-reg, which mostly fits linear regression, or proc-logistic, which fits logistic. Proc-genmod can fit linear or logistic or log binomial or Poisson or a bunch of others. So it's a general modeling procedure. And the main process is this. You include the two components of the interaction, rural and lower education, include them as separate terms. That's really important. And then you also include them with this asterisk between them. And this term here says, is there anything going above and beyond? Is there any causal effect or any association above and beyond the association that's attributable to just being rural and just being low education? So that's what's happening in this part of the model. There are two models here. The top one is for estimating risk difference. This is an additive model. And the bottom one is for estimating risk ratios. This is a multiplicative model. And the only thing I did to make that happen was I changed something in the link function. All right, so when I say link equals identity, what that means is don't make any transformation like a logit transformation or a log transformation. Just leave the numbers as ones and zeros. Leave them as they are. But because I said dist equals bin, which means the distribution is binomial, I think that Mike went over statistical distributions in that stats review that would happen before the course. Binomial is the kind of distribution we use when data are ones and zeros, true or false. Since it's binomial, it's appropriately accounting for the fact that our numbers are ones and zeros. They're not, like continuous from minus infinity to infinity or something. So the link equals identity is how we get the risk difference model. And then if we change to link equals log, then we're going to get the log risk. And if we exponentiate the output, the beta coefficient, we will have the risk ratio. So for this one, we don't need to exponentiate. We just take it. The numbers that come out are going to be risk differences. And in this one, if we exponentiate, the numbers will be risk ratios or prevalence ratios. And of course, the alternative that if you've done proc logistic, or if you set this to link to logit, is you would get an odds ratio when you exponentiate. This is one of those points where if you feel a little lost, that we're in the weeds right now. We're gonna come back out. The big question that we're asking at this moment is there effect modification? Is there a different effect for women with low versus high education? So if you feel lost, take a deep breath. We're going to be right back with you. And this is just an example of the output. In this case, this is the output specifically from the risk difference model. I'm going to talk a little bit more in a minute about interpreting these, but again, these are literally risk differences, like a 7% risk difference for rural versus urban. That's how we interpret that. But the reason I printed this table is because this p-value for the interaction is 0.63. So there's an estimate for the interaction, but it's quite imprecise. The standard error is twice as large as the estimate, and it's very non-significant. So what that means is I wasn't qualitatively very convinced that the stratum were very far apart in terms of the risk difference. And now I also have statistical evidence that says, yeah, there's not much evidence to support that those are really two different numbers, given how much data we have. I want to pause there, partly just because I've been talking nonstop, and just see for anybody who feels like they can articulate a question. Again, if you're feeling in the weeds, we're going to come back a minute. But if you feel like you can articulate a question, are there any questions about particularly this notion of effect modification, which is, I think, both super interesting, but also a little kind of complex and mind-bending. So let me take a drink and you unmute or put something in the chat if you have a thought. All right. All right, I'm gonna keep going then. Okay, let's just remember where we were. We had a question that helped us go through these first few steps. We estimated the occurrence of preterm birth, both in rural and urban. We estimated the measure of association, which really is just an unadjusted, crude, descriptive measure. And then we had these next two steps. And first we did effect modification, and now we're going to do confounding. I'll just say a word about why are they in that order. In reality, sometimes these two get tangled up together. We're doing them together. But one reason is because if there is effect modification, then it's important that we not treat the variable like a confounder, that we not just adjust for it. We actually want to report the answer separately for women with low education and for women with high education. And so that's why it's important to start there, because if there was something different going on, if we ignored that, we basically would take an average across the two and we would miss what might be a really important finding. And why might it be important? Again, if there was differences between women of different education levels, it might suggest that things related to social status or socioeconomic status are part of what's making rural environments more deleterious. So maybe the issue is transportation, or it is doctors who accept Medicaid, or it's appropriate referral, et cetera. That may be something that women with a higher education were able to overcome and women with a lower education weren't. So the reason we don't want to just average over it if it were there and meaningful is that it might actually inform something about an intervention or a modification to the program, or help us understand why is this rural-urban divide happening. So that's why we start with effect modification. But again, when we've got more than just these three variables, the exposure, the outcome, and then the education variable, the covariate, when we've got more than three variables, these two, confounding and effect modification, might get a little more intertwined. Okay, we have determined, based on both our qualitative and our quantitative evaluation, that we don't think that there's effect modification. It looks like, to the best that we can determine, there's not a meaningful difference in the rural-urban disparity based on maternal education. So let's think about how to get the least biased estimate of our causal association. And when I say least biased in this particular point, what I'm really saying is, how can we address what might be important issues around exchangeability or imbalance between the women who live in rural areas and the women who live in urban areas. We might think that there's things that are not just about healthcare access or social environment that make them different, and those might be spurious reasons why we see the association. So what we want is an unbiased and not spurious estimation of how those two things go together. And so how can we do that? And that's going to be the process of seeking out and addressing confounding. Before I do that, I do just want to say a few words about error generally in epidemiology. So we're going to talk mostly about confounding, but that's not the only source of error. This, I suspect, is probably review for a number of people, but I just want to make sure that we recognize that there's kind of two big buckets of error, right? We could be wrong just by chance alone, and that's random error. And that, again, is very related to sample size. So just by bad luck, the sample that we took is not like the true underlying sample. If we were to take a bigger sample, the bigger it got, the closer it's going to be to the true underlying sample. So that's random error. But the kind of error, and this is where p-values tell us something. They tell us something about the role that chance might have played. What p-values do not tell us about is this systematic error. And this is where epidemiologists gnash their teeth and stay up late at night worrying about whether we have undiagnosed or uncontrolled systematic error. So this can produce small or large bias. So again, bias is when the answer that we got is not the same as the true answer. And what's really important is we can never fix systematic errors by having a larger sample size. So we could do bigger sample sizes to fix random error, but the systematic error needs a different strategy than just bigger sample size. So we either have to do a better job of designing the study. Maybe it's about measurement, maybe it's about how we sampled people, who we selected, et cetera. And or we need to make sure we do the analysis that corrects for the things that we weren't successful in fixing in the design stage. And one strategy that can be useful is multivariable analysis. So that's where we're going, obviously. This picture on the right is one that's often used to just visualize the difference between random and systematic error. So random error is also about variance, low variance. So this is low random error because all the points are very close together in this target shooting, as opposed to high variance. So the points are far apart for whatever reason. They're not just by random chance, but they seem to be spread out, right? So random error is shown there. And then bias is not just how close together the points are to one another, but how close the points are to something that we might hypothetically know or believe exists in the universe to be the true value in the population. So obviously this one is what we would like, low variance and low bias. But what's possible is we could have low variance and maybe super significant p-values and be super excited. What this means is we are really consistently wrong every time we take the study, right? Systematic bias means we do the study over and over and we're wrong in the same way every time. So highly significant p-value and we're always wrong. In contrast, here's one where maybe the p-value is not so significant, but all the points are at least in the right space, right? So we're actually, this is a low bias situation where any one point isn't right, but together, you know, are not so bad. And then this one isn't very good, where we have both high bias and high variance. Okay. This is just saying again that sample size, study size, which is on this axis, fixes one of the two sources of error. If you have confounding, having a bigger sample size won't fix that. But if you have random error, having a bigger sample size will. And if you got to infinity, we would, if we had the entire population, then it's no longer a sample, then we have a census, right? So if we had all of the data possible for all the points in time and every person, then there would be no error. But systematic error is the one we're concerned about. So this bias, it's a flaw in the design, or perhaps in the collection, or perhaps in the analysis, but ultimately it leads to the wrong conclusion. Certainly it can lead to the wrong number. The wrong conclusion means we say something is related when it's not, or we say something is not related when it is, or maybe the most extreme is we say something is definitely bad for you when it's definitely good for you, or vice versa, right? So we don't want those things to happen. Of the systematic errors, there's three things that we often talk a lot about: confounding, selection bias, and information bias. I'm going to talk about confounding a lot today. Selection bias, this is when the people who are in our data set are not exactly like the people in the source population. It's a little, it sounds like it's asking the question, are they representative or not? But it's actually a little bit more specific than that. It's that the ways that the people in our data set are different, those ways are related to both the exposure and the outcome. So somehow they actually create some mixing up of associations between the exposure and the outcome because we selected people. And a common way that this happens is when we do convenience samples from people who are willing to participate in surveys. People who are willing to participate in surveys are different from people who don't participate in surveys. And if the ways they're different are related to the exposure and the outcome, then the answer we get from the survey won't actually tell us about what's really happening in the population. So that's the concern with selection bias. Information bias is about whether the strategies and tools we use to measure things worked well. In other words, did we correctly figure out who lived in a rural versus an urban area? We might have misclassified some of them. So for example, if you accidentally used on the birth certificate, the event county code rather than the residence county code, it may be a lot of women, excuse me, especially high-risk women, delivered in urban areas because that's where the tertiary care center is. But they were from rural areas. They got transferred there because they got to an appropriate level of care. So that would, if we accidentally did that, that would be a source of misclassification. We would have put people in the wrong cell in our 2x2 table. So information bias can happen by misclassifying the exposure, the outcome, or covariates. Both of those are really important, but I'm not going to talk a lot more about them today. I'm going to talk about confounding. So confounding, let's go back to our directed acyclic graph. This one looks almost like the previous one, except I added this one more arrow that goes from education to rural. So confounding occurs when there's a third variable. In this case, the third variable is education. And that third variable meets these criteria. It is independently associated with the outcome. So we actually know with pretty robust evidence that maternal education is related to preterm birth. Exactly how that comes to be is probably a complicated process that has to do with a variety of things about stressors and social support and access to information and access to healthcare and a number of things. But even when we control for health behaviors, health insurance, entry into prenatal care, we do see this gradient. So that's one part of confounding, is that the variable needs to be related to the outcome. It also needs to be related to the exposure, and specifically in a particular direction. This needs to be predictive of or causal of the exposure. You might ask, how is individual education a cause of rural urban status? I'm going to talk about that in just a second. And then the third criteria is that it is not an intermediary. In other words, if this arrow were reversed, if rural urban actually caused your education, which, to be clear, you could make an argument that the school qualities in rural areas might be different than the school quality in urban areas, and so your opportunity to achieve higher education might be systematically caused by living in a rural area, but I'm not going there right now. But if the arrow went the other way, this wouldn't be a confounder, it would be a mediator. So confounding meets these criteria, that the confounder is independently associated with the outcome and with the exposure, and it's not an intermediary. So our question is, when we see a structure like this, is how can we get an unbiased estimate of the rural preterm birth association? In other words, we have this correlation, but to make it causation, we somehow have to deal with the fact that we've got confounding. Oh, here I'm explaining what I used as shorthand here. Sometimes we have variables like this where we say the arrow goes from here to here, and you think to yourself, if I have a college degree, that doesn't cause rurality. Really, that's a shorthand for maybe there's some unmeasured variable that both affects your education level and also affects where you live or affects your in or out migration. So this shape like this is exactly the same in terms of causal inference as this shape. In terms of, this is still a confounder. It's just here I'm being a little bit more explicit that I know education doesn't cause rurality, but I think that there may be an imbalance among rural women compared to urban women because possibly there's some prior factor. Just as an aside, when people are thinking about social determinants of health and health equity questions, and they have a variable here that is essentially a social construct like race, to say that race causes preterm birth is unclear because it's not quite clear what it means for race to cause that, because we can't intervene on race. It's also unclear what it means to say education causes race. But what we can sometimes say is that there's a complicated set of historical processes that induced a correlation between race and education, or between rural urban status and education. So this might be not just one thing, but it might be a history of investment or disinvestment in parts of the state, a history of Jim Crow, a history of segregation, et cetera. Okay, so that's just a little aside there. In our confounding, remember I told you that the arrows in these DAGs, they represent causal relationships. We're basically, even though I just told you this is like a shorthand, we're basically saying somehow education causes preterm birth. Granted, exactly how it causes it, there's a lot of nuance in there. So all the arrows represent causal relationships, but in terms of our one specific question, which is does rural-urban cause preterm birth? This is the causal relationship we're interested in. And so this red path is called a backdoor path because I can get from rural to preterm birth without going down the green path. That's basically what confounding means, is there a way to get from the exposure to the outcome that isn't through the causal path of interest? And if there is a way, that is confounding. That's the thing that we're trying to prevent. And we have tools to prevent it. Most of the statistical tools that epidemiologists use are really focused at addressing confounding. So that's partly why I'm talking about this so much. Certainly we can correct for confounding in the study design. That's actually the most powerful way to address confounding. Some of the things people do are matching or restriction, but there are times, for example, in lots of observational research in maternal and child health where that's not an option. And so we need to use analytic tools to essentially statistically produce the counterfactual world, the potential outcome world, where we look at the effect of living in a rural area on preterm birth, and then we imagine that exactly the same people were exposed to an urban area, but everything else was held the same. So we control for or hold constant the confounders to estimate that unconfounded relationship. And we have tools for that, like stratification, which we're going to look at in a minute. Standardization, if you've done any kind of age-adjusted rate, you've probably done standardization. Regression, which we're going to look at. And then I mentioned G methods are kind of more advanced methods. In a DAG, one of the common things people do when they choose to control for something, they put a box around it. And basically, you can imagine that that box is blocking this path. So I still want to have education on my DAG because I'm saying I recognize it's a confounder, but I put a box around it. So if this DAG right here were the true world, then whatever estimate I get is the best approximation of the true causal effect. If, this is a big if, this were the true DAG, in other words, the only confounder was education. Oh, so let's actually think a little bit more about how simplistic my DAG is. Let's use the annotation tool just for a minute, just to wake you up a little bit. Let's use the annotation tool and just make a list of what other things might be confounders now that we've talked about this idea of confounders. And you could either just type them like we've been doing, or if you want to use the draw tools and try and draw arrows, you can do that. That might get messy, but it'd be fun. So let's think about what are other possible confounders, given now that we've had a little more conversation about what the causal effect of rural urban might mean. Right, so we've got access to higher level care, age. Transportation, race, distance of travel, all right, keep adding as we're going, but I'm going to just make a few comments. Health insurance, okay. one of the reasons that I like DAGs is not just because they're a tool for us to use individually in our own little cubicle, but because they're a tool that we can use to communicate with other colleagues about our assumptions. And a lot of times when we do that, it spurs people to question our assumptions. And that leads to conversations that hopefully lead to better analysis. So I'm going to question some assumptions. Why do you think there might be a greater distance to travel in rural areas? And I don't mean to just pick out this person, but why might there be a greater distance to travel to get to a birth center? Any thoughts in the chat or unmute? Or relatedly, why might transportation be different in rural? So okay, so Katie says maybe there's declines in hospitals in rural areas. That's definitely happening in Georgia right now. We have regular OB hospital closures in rural areas. Rural resources are less populated, have fewer resources. No public transportation options. Okay. Thank you. That's great. So this is exactly what I might do sometime. I might say, okay, I've got this association between rural and preterm birth, and I think I should adjust for transportation and distance to travel center. And I would make this DAG, and somebody would maybe say back to me, I think that transportation and distance to travel are actually on the causal pathway. Maybe they're mediators, because the arguments that we have in the chat is that the rural actually causes, there's something about the rural environment, for example, less dense health services, that makes a further distance. And so that conversation that we might have together helps me avoid accidentally, unintentionally controlling for something that isn't maybe a confounder, but is actually part of the effect of interest. Now, I do want to be clear, I made this tricky by making the exposure rural-urban, which is, again, not a nice discrete thing like taking aspirin versus not, or smoking versus not. It's a complicated socio-contextual historical phenomenon. So it's hard to say for certain, what do you mean is a consequence of rural-urban versus is correlated with. But I might argue that the three on the top here, access to higher level of care, transportation, and distance of travel to get to birth center, all three of those are plausibly on the causal pathway, and that would be a good reason not to adjust for them. Because we would like to know what's the, essentially, maybe another way of saying it is when I ask the question rural-urban, maybe what I should do is I should refine my question, like, is access to transportation and access to level of care, geographic spatial access, is that a cause of preterm birth? And then I would more explicitly say these are in fact the exposure or part of the pathway. Now, age and race, I think, are interesting too. I could argue either way. On the one hand, in many states, there's some difference in the age distribution in rural and urban areas, and often a large difference in the race distribution in urban and rural areas. And because race is strongly related to preterm birth, that could be a backdoor path. That may be a spurious finding. So that adjusting for race is something to consider, but I'm a big advocate for being super cautious whenever we use race in a regression model. In other words, we should think clearly about what is it we're doing by controlling for race. Because race is, again, a social construct. It's describing an identity and an experience, and it's related to history. So what are we doing? And so it could be by controlling for race, we're saying that we don't think that the social environment that makes rural counties unhealthy is necessarily related to, for example, the historic process of segregation. If we could say that, then maybe race is strongly related to preterm birth, but race is not necessarily, is not a mediator, and there's not some other mediation pathway. So then the fact that there's a difference in the distribution, that there's perhaps a larger white population in rural counties than urban counties, might be a reason to control for it. But I think that should be, that decision should be done with care. Health insurance, on the other hand, unless the process of enrolling people in Medicaid or providing access to health insurance is geographically disparate, health insurance does seem like a good candidate for another confounder, because it is possible that there's differences in health insurance, but maybe that's not just about, you know, kind of the rural environment, but it's about other things of people who live in rural areas and urban areas. If it sounds like I'm being wishy-washy about how you choose variables, that's super intentional. We should be critical of how we choose variables. What we definitely should not do is one of those statistical procedures that tests every possible combination and tells us the variables that are only statistically significant, because that lacks any input from theory, from prior knowledge, from our common sense. So what we want to do is struggle with the questions of what variable is important when we're talking about confounding? What variable is a plausible effect modifier? All right, thank you for that. Let me just clear these. There are several ways to address confounding. Again, you just identified several other variables that we could have discussions about for confounding. We're going to stick with our simplistic world where the only confounder is education. And if the only confounder was education, we could try to address it in a simple 2x2 table strategy called stratification, stratified analysis. This approach is nice because it lets us see what's happening. It's not like a statistical black box where you close your eyes and smoke comes out of your computer and it gives you a number. You know, you have an understanding of where it comes from. It, however, is limited when you get more variables, or particularly when they're not simple binary or, you know, just a few categories. So I'm going to talk about stratification, but then I'll also talk about how to use regression models to adjust for confounding. So the stratification idea looks a lot like what we did with effect modification, right? We made a separate table of the relationship only among women with low education, and then a separate only among women with high education. Now, the idea here is by separating these women, we're obviously within one of these tables, there's not confounding by education. A caveat to that is assuming education were simply binary, that there's only low and only high. Of course, there could still be differences within the categories, but putting that aside, there's not confounding within. So when we estimate our measure of association just among women with low education and just among women with high education, what we get are estimates that are not confounded by education. However, we've got two numbers and we've already determined that there's not effect modification. So that means what we want to answer, we want one number for our answer. And the way that we can do that is basically by figuring out, remember we said the reason confounding happens is because education is unevenly balanced in rural and urban areas. So it was associated with rural urban because of that uneven balance, and therefore it caused this backdoor path. We kind of want to break that arrow that went from education to rural urban. So we want to balance the rural urban women with respect to education. And we can do that through something like weighted averaging. We basically average these two numbers together, 1.46 and 1.64, or 0.095 and 0.073. We average them to get the answer that would have happened if there was an equal number controlling for, holding constant, the distribution of education. The question is, how do we do the weights? We can use something called a Cochran-Mantel-Hansel statistic. So that is essentially a pretty elegant statistical solution to do weighted averages when you have something like confounding. And we can get SAS to give us the Cochran-Mantel-Hansel statistics just by putting CMH in this proc-freq line. So I just want to point this out. This is proc-freq, which is used for tabulating tables, like making 2x2 tables. And the way it works is the last two variables represent the 2x2 table, so my outcome and exposure. And this variable that comes first is the stratifier. In this case, it's the confounder, okay? Apologies, I don't have examples of code in Stata or R that do this. I do think that Mike has some really nice supplemental material that was in one of the Teams folders that has some sample code for many scenarios, including, I believe, frequencies, and I think it includes some Stata code. If not, if you work in something other than SAS and you want to know how to do this, one of us will know how to do it. So this is relatively simple, and what it's going to do is give us a table like this. So remember, we're interested ultimately in the risk ratio, rural, urban versus preterm birth. And from our previous slide, our crude or our unadjusted answer was 1.7 about. And this relative risk column 1, this is the Mantel-Hansel adjusted risk ratio for the relationship between preterm birth and for rural, urban, and preterm birth. So it's 1.49 with a 95% confidence interval. So this is one way that we can produce an adjusted risk ratio. That's where we had this one confounder and it was nice and binary. We maybe could try, we certainly could have an education variable that perhaps had 3 or 4 levels, and this would still work. But if we had more covariates, this becomes much more challenging. So if you have more confounders or many levels of confounders, this stratification approach stops working so well. So that leads us to our strategy number 2, which is to try a regression model. Okay, so again, regression modeling isn't something just to jump into if you've never done any of it before. The code that I'm including here in the discussion is hopefully useful for those of you who are using regression modeling to some degree and are interested in using it in new ways, or maybe many of you are already doing it in these exact ways. But this isn't intended to be an exhaustive discussion of how to go about fitting and interpreting regression models if you've never heard of them before. Just as I did before, I'm going to show you how to do this with a ratio model and with a difference model. In other words, the link is log, the link is identity. We're going to produce risk ratios or risk differences. So I want to point out a few things here. This is the same as we pointed out before, the link equals log, link equals identity. I just want to say out loud so that you understand, because you could code your outcome in different ways, but I've coded my outcome as 1, 0. So births that were preterm are coded 1, and births that are term are coded 0. The way GenMod works, it actually, by default, would estimate the probability of having a term birth, but I actually want it to be the probability of having a preterm birth. So preterm equals 1. So this descending means do it the reverse of what you were going to do by default. That's just a silly SAS thing. There's lots of silly SAS things. I don't know why they did it that way. So that's explaining why I have that code there. And I mentioned before that in the absolute models, the identity binomial, which the output that we get is just directly the risk difference. Like we don't have to do anything to it. It's just right there for us. But in logistic models and log binomial and Poisson, the output from a proc GenMod is actually on the log scale. So you wouldn't want to just report the number that it spits out automatically. So you could either just use your calculator and exponentiate it. I'm going to show you that in a second. That would just be, if you exponentiate the beta, it's going to give you the risk ratio or prevalence ratio. Or you can use this line here. So that's all I'm telling you in this little box is the estimate statement. When I say rural 1, I'm basically saying, tell me what is an estimate of being in a rural 1 versus rural 0. So rural versus urban place. And then I put this EXP, which means exponentiate. So just a little bit about the interpretation. In the case of the log binomial, again, these things under the word estimate are called the beta coefficients. The intercept is one we don't usually interpret a lot, although it is essentially the log risk of preterm birth for everyone when the rural variable is set to 0 and the low education variable is set to 0. But that's not something you need to interpret most of the time. And then what these two represent are the log risk. Again, this is on the log scale. The change in the log risk for preterm birth for women who are in a rural area, rural 1, versus urban area, rural 0. So it's 0.41. And then this is the change in the log risk for preterm birth for women who are low education versus high education. What's great is because we ran these in the same model, this 0.4172 is automatically controlling for education. So this is an adjusted estimate of the log risk of rural urban. Now, you don't probably want the log risk. As I said, it's hard to interpret 0.4172 on the log scale. So you could just exponentiate it with your calculator, or because we did that estimate statement, you will also get this output down here. And this is the risk ratio. So in other words, if you had a calculator and you exponentiate 0.4172, you will get 1.52 about with this confidence interval. So this is the risk ratio and the 95% confidence interval. So that now becomes an adjusted estimate of the relationship. And if our DAG were true, that is our best guess at the causal effect of rural urban on preterm birth. And just once again, from the binomial identity model, the risk difference, these are literally risk differences. So the intercept is interpreted as the risk or prevalence of preterm birth among women who have rural equals 0 and low education equals 0. In other words, among urban high educated women. And then 0.836 means that women who live in a rural place have an 8% higher risk than women who live in an urban place controlling for education. So it tells us sort of directly that ratio. And then if you're interested in statistical significance, there's p-values there. Okay. Mike has a comment. Supplemental code document does include SAS and Stata code. To find it, yes. Okay, so Mike gives instructions on where to find it. That's great. I thought it included Stata code as well. I mostly work in R and I work in SAS a little bit, but I know more of you work in SAS than R, and I don't know anything about Stata. So in the Venn diagram of those 3 programs that most people use, many people use, between us, we can cover all of them. Okay, we spent some time in the weeds. Let's just take a deep breath, see if we can figure out if there's something to salvage from this, if you felt like the regression was too far down there. So the big picture, what was the question again? What are we doing here? So we know that preterm birth in rural area is higher than in urban areas. We know that descriptively, right? We observe that the risk is higher. But the question was, is it causal? So what we did, we defined a population, an exposure group, a reference group, and an outcome. We took a sample of them and we estimated the measure of the risk and the measure of association. Really importantly, we spent some time, possibly we spent a lot of time thinking about the conceptual framework, the causal structure. And we informed that thinking not with p-values, but with theory and prior evidence and expert knowledge. We used resources. So we talked to people, we learned about stuff so that we got as good an idea as possible of 1 or 2 or 3 or half a dozen different interrelated versions of the causal structure, the conceptual framework. Given that process, we then went about testing some specific things that arose from our DAG. We asked, I wonder if there's effect modification by education. In other words, I wonder if the rural-urban effect maybe doesn't matter as much for high educated women as for low. And the answer was, we don't have evidence for that. Okay, so that was a question, like a sub-question within the bigger question that we could answer. And then we said, okay, we recognize that the crude estimate is probably biased because of confounding. So can we get an estimate controlling for confounding by education? And so in that way, we're basically saying maybe it's not only about the sort of transportation, healthcare access, but maybe is there something about the risk profile like education? So by controlling for that, we got an answer that could be a better estimate of what the true causal relationship is. Why would that matter? That would matter if we were thinking about intervening, changing. Like, what if our goal was to make the health environment in rural areas equal to the health environment in urban areas? That would be a hard sell. Part of what you would need to make that sell is to say, we know that the preterm birth rate will go down because of that. But the only way we could know that is if we were relatively confident that that's a causal relationship. This is just a summary of all the numbers we had. So we started with a crude risk ratio of 1.73 and our adjusted risk ratio is 1.52. So importantly, the answer is not, it's not like in a different direction or anything, but it doesn't have to be, but it commonly is that once you adjust for confounding, the measure of association becomes smaller, like closer to the null value. Similarly, on the absolute scale, there was an 11% excess risk in rural versus urban areas, but controlling for confounding by education, there's maybe only an 8% excess risk. Okay, so that kind of process of doing those steps, but then also remembering at the end of the day, that's kind of what we're trying to do, is figure out, well, which of these numbers is true? What's the logic behind why I would pick one over another? If I thought that there was confounding, then these are the correct ones because they address confounding. They haven't fixed every source of error, but they address confounding. So I think I just said that. All right, and I said that. What I want to do, I know I'm running a little short on time, so what I want to do is make a few comments about variable selection. If you find you are someone who does work in multivariable regression regularly, you undoubtedly have had the dilemma of picking, what should I adjust for? When should I put a variable in the model? When should I not? And many of you know, and others who don't know, there are programs that are written in SAS and probably other software that will do some stuff automatically for you. It works well for predictive modeling, but for etiologic modeling, it doesn't work well. So what we don't want to do is use some kind of rote algorithm. So here I've summarized 5 kinds of variables that play a role in your model. 2 of them are the obvious no-brainers. We need an exposure and an outcome because that's what shapes the question. We're interested in whether modification of this variable results in a change in this variable, right? So those 2 are straightforward. We just spent a lot of time talking about confounding. Confounding is when confounding will cause a spurious biased association, and therefore we want to stop confounding. So if we have a confounder, something that's fitting this criteria, then we definitely want to keep it in the model. We must adjust for it. But these 2 variables here, M and L, are 2 kinds of variables that if you were to do a statistical test and say, is M correlated with E and is M correlated with Y? Or similarly, is L correlated with E and L correlated with Y? If you were to do those 2 tests, the answer would be yes. And if you use that as your guideposts for when to include variables, you would choose to include these 2. The problem is, by adjusting for them, you would actually get the wrong answer. So sometimes people feel like the more you adjust for, the better. Definitely not true. You want to adjust for things that give you an unbiased estimate. If you adjust for this mediator, you may actually block a lot of the causal effect of the exposure, and you might misinterpret the result. And again, I'm not going to go into detail now, but this is called a collider, and it sometimes happens from selection bias, but can happen for other things. And it can be another source of bias. So the take-home message from this is, just because variables are correlated with the exposure and correlated with the outcome does not mean you should adjust for them. So there are 3 strategies that people use to select variables, and I'm putting them in, I color-coded them by the importance I think that they should have. I guess I put them in inverse order of importance. Statistical testing, that's the one where you basically test if maybe you've got a list of 15 covariates and you see if they're each associated with the exposure and each associated with the outcome. Don't do that. And the reason is because you will you won't inevitably, but if there are variables that are mediators and colliders, you likely will include them and you will get a biased answer. So I only put this here because a lot of people do it, not because it's something you should do. It's in red, bad. Okay. A very common strategy is a change in estimate strategy. And I have this sort of intermediate. This is where you have a model that controls for all the variables you think are important, and then you take one of those variables out and you fit the model again, and you look to see if the relationship between an exposure and an outcome changed, say by 10% or more. With the idea being that if it changed a lot, maybe that variable was important. And if it didn't change much, maybe it wasn't important. I have this as intermediate because it is still a data-driven approach, but it's valuable because a lot of times we don't have good prior information to pick what is the best set of confounders. So sometimes a change in estimate strategy is okay. But what I have as sort of the ideal, which again is not always possible, is a knowledge and theory informed selection, not a statistically driven selection. We use theory, prior knowledge, expert information, and the careful, thoughtful interrogation of a DAG or other conceptual models to understand which variables are mediators versus confounders. Where might we have collider stratification bias, etc. All right, I have a long soapbox about p-values, but I do want to, I see it's at 3:50 and I'd like to have, I can't remember if we end at 3:50 or at 4, but I want to have a minute or two. So I'll give you the short version of my soapbox about p-values. They're not meant for what we use them for a lot of the time, right? What p-values tell us is they tell us that a particular test statistic is as large or larger than we would have expected if the null hypothesis were true. And they're basically telling us what's the likelihood that chance played a role. So the p-value tells us something about the role that chance played a role given the test statistic we have. So the things that drive p-value are how unusual are the data given the null. So that's good. We do want to know, are our data different from the null? But they also are strongly driven by sample size. A very small difference in meaning could become statistically significant in vital statistics because we have such large sample sizes. So p-values can mislead us. P-values do not tell us the probability that our alternative hypothesis is true or the probability that our findings are important, okay? P-values have become such a problem that the American Statistical Association, i.e. the people who invented the p-value, had to put out a statement that said, stop using the p-value this way. It was never meant to be used this way. In fact, they said, here's 6 principles for use of the p-values. I've highlighted several things that I think are particularly important. But one of them is that policy decisions should not be based only on whether a p-value passes a specific threshold. And p-value does not provide a good measure of evidence regarding a model or a hypothesis. I'm not saying that p-values are useless. What I'm saying is we should use other kinds of reasoning, including information about the magnitude of effect and the strength of our study design. And we should use other kinds of reasoning in alignment with it, along with p-values to make decisions. That we should be hesitant to just throw out a model because of a p-value. And finally, a take-home message. So Wednesday, we talked a lot about descriptive epi. Descriptive epi may be all you do, and that's great because it's super important. It's describing how the world actually is, how you see it. This is how it's changing year by year. It helps inform resource allocation. It helps us identify emergence of new problems, etc. But you may begin to, or you may already be working in analytic epi. And when we do that, it's one step of many in the process of describing why the world is the way we find it. What's happening? What's the cause and effect? And in particular, we're interested in consequential analytic epi. Is there an intervention or an action that can be informed by the answer to our question? Can we test something that could lead to improved policy, improved program? So when we're doing analytic epi, we need to define a specific and testable question. It sounds straightforward and sometimes really hard, and sometimes a step that people skip and they jump right to data analysis. I don't even know what they're analyzing if they don't have a question, but we all can do it in lots of different ways. Develop a theory and evidence-informed conceptual model, and then systematically describe the data, starting with crude associations, carefully thinking about different other causal effects like effect modification and addressing bias. At the end of the day, we'd like to be rigorous and diligent and also humble, because probably my model and your model are wrong, right? All models are wrong, but some of them are useful. That's the saying. So what we would like to do is produce the most rigorous evidence we can, and also be humble about the limitations. And with that, I am going to stop and say, apologies that we are right at time, but if there are any questions or comments, I would welcome them.
You're welcome to use the chat or turn on your video, unmute. Katie says it was helpful and thank you.
So I will say again what I said in the beginning, which is that 2 hours isn't enough to absorb and digest everything about anything probably, and certainly not about multivariable analysis. So think of it as sort of levels of learning, and at the outer level is how do we ask questions that matter, and then how do we go about preparing information to analyze them, and then if you're the one who's involved in doing the analysis, how do we kind of proceed through steps that can help us provide answers that are useful. If you are at one of those stages, but not quite at the next one, that's an opportunity to reach out to one of us and talk about an idea, like I'd like to do this, or reach out to somebody in your workplace. It may be that you have colleagues who are doing this, and this is, now that you kind of have like a little bit of a handle on it, you can sit down and say, okay, I know I'm supposed to do something or other with, effect modification, but I don't quite totally understand that, and have conversations with them. So that sort of process would be, that would be a positive outcome in my mind if that happened too. Work to absorb this better. Yes, that is a process. All right, and then definitely, I'm unfortunately going to miss it because I'm traveling, but attend Mike's roundtable on multivariable regression and pepper him with lots of hard questions. All right, so Ashley and or Mike.
Just a couple of quick things for next week. The session on Monday is about evaluation, and we're going to learn a lot from Pat about how to basically be better epidemiologists when it comes to thinking about the programs and policies that we work with. She does have a couple of videos posted in the evaluation section of the teams, so please check those out before the session on Monday. And then on Wednesday, we'll talk about data communication. I do have a video posted there in the data communication section of the teams, so check that out too. Pat, anything else you want to say about the session on Monday?
Oh, sorry. No, thanks for plugging the video, and look forward to talking to you about evaluation on Monday.
All right, I'll shut up and turn it over to Ashley. Thank you, everybody.
Yes, and just a thank you to Dr. Kramer, and I think Mike wrapped it up well. You'll get an email from me as a prompt reminder. Hopefully take some time to review the videos before Monday. And again, join us for as long as you can for the roundtable discussion. My inbox is open if you have questions or any issues with accessing anything. And then again, another reminder to complete evaluations as we're taking that and those responses into account as we go forward. And you'll know more about our speakers coming on Monday, hopefully, about our social determinant of health panel discussion, which we're really excited about. The information will begin to be loaded there. So it is a little bit longer of a session next Friday, but we really anticipate some great opportunity to be in discussion with each other and hold that space with two really amazing women. So we will see you all on Monday.